And hello, welcome back. Okay, things should be running. Yes, I have volume. Yes. Okay, so welcome back to this video. As I was saying in the last video, we are doing some Sparlot-Almaraz boundary conditions. Unfortunately, making Sparlot-Almaraz boundary conditions that's not as straightforward as say a what do you call that? The k omega SST or kEpsilon method. For k omega SST and kEpsilon, you can just, especially for the inlet, you can just specify a turbulent kinetic energy based on some intensity, and then OpenFOAM will just calculate everything for you. That's very convenient. And the same goes for omega and epsilon. You have this mixing length. Okay. Yeah, so you don't have the same, you have it for k, you have it for epsilon, and you have it for omega. So if you take a look at omega, is exactly the same. So not really much of a change there. Alright, whether it's for RANS or such. Okay, if you go to the Sparlot-Almaraz case, you won't have the same equivalent, right? You won't have the same equivalent. So you have to use something along the lines of a fixed value. And to calculate this fixed value, one good way is, again, well, if you take a look at the kEpsilon model. Okay, where's the kEpsilon model? Hold on. Let's do kEpsilon model OpenFOAM. Alright, and you will have it in the guides here. Okay, so I'll just do the very basic. Okay, kEpsilon model, I guess you can actually use sort of a guesstimate by nuT. Use nuT as your guesstimation for what nuTilda should be, because I explained that they're very similar. Though nuT and nuTilda, the only place that will differ is near the walls. Otherwise, they're quite similar. Okay, so k is here and epsilon is here. And I guess after some time flowing through the pipe, the value will stabilize. So, I mean, regardless of whatever. Okay. Anyway, pardon me, I took a break, so I kind of skipped a bit front in the video. But anyway, yes, so we have to use a fixed value. There's no easy way to do it. And one of the easy ways to do fixed value is to use this formula. This turbulent viscosity, because nuTilda and turbulent viscosity, they're almost the same. Okay, almost the same, except near the walls. So we'll have to find a way to do the calculation of this k square and epsilon. Both of these can be found through this kind of formula, where you have 3 over 2 I, which is the turbulence intensity. We kind of set it at 0.05, and uref. Uref is the what do you call that? I think the reference flow speed, which is usually the mean velocity in the pipe. So if you really want to do it, so I guess you can use this LibreOffice, or in this case, you if you're on Windows, you use Excel. Nothing too bad with that. Okay, this is stuff I need to get rid of. Let me open a new one. Yeah, this is much better. Okay, so this one now closed. Some other files I'm working on. Yeah, let's get started. K, so you have 3 over 2, okay, equal 1.5. No, that's not the way. Okay, that's better. Okay, let me zoom in, and so that you can see better. You just do a very quick one, 3 over 2 I uref squared. Okay, so I and uref will be there. This will be I, this is uref. So this is well, depending on the what the Reynolds number in the pipe is. I can change it around. So Reynolds number, I think, is equals to uref times L. Okay, that's the length scale. What's the length scale? Can't remember how wide the pipe is. Let's see. Paraview. See the axis grid. Okay, the pipe is okay, let me see. Okay, that's not, yeah, that's better. Okay, let's zoom in. We'll go up, pan up, and zoom in. Okay, pipe is 0.01. Yeah, 0.01 meter long. Okay, let's put a L. 0.01 meter. Okay, this L pipe. Okay, then okay, let's see how much time do I have remaining. Okay, I still have about 14 minutes. So, okay, before I hit the 20 minutes mark. But anyway, so Reynolds number is uref times L over the turbulent, no, the kinematic viscosity. What's the kinematic viscosity? I can't remember. Transport properties will be here. 1 times 10 to the minus 6. Okay, so this fluid has a 1 times 10 to the minus 6 nu. So let's just put that. I'll put a nu here. 1e minus 6. And Reynolds number will be this uref times this pipe. Okay, pipe divide by nu. Okay, so 0.1 will be 1000. 0.2 is 2000. Let's put a 0.4. Okay, let's put a 0.4 to be our Reynolds number. Okay, and then the I should be around 0.05. It's pretty arbitrary for us. Okay, so K will be 1.5 times I times uref squared. So this is the K value we will get. So let's save for now. Yeah, maybe I can save a copy inside the folder so that you can see. It's in ODS format. It's an OpenOffice document, but should not be too much of a problem for Excel to open up. Okay, so I will put nuTilda. Okay, no, shucks. Let me go back there again. nuTilda calculations. All right, nuTilda calculations. nuTilda calculations. Okay, so I'll say nu t equals to c mu times k squared divided by epsilon. Okay, so this okay, nuTilda is, well, our set is, okay, I will say it's approximately equal to nu t. Okay, that's all. All right, so let's do nu t. Okay, nu t is, all right, we will need to calculate that later. We will need to also calculate epsilon. Epsilon is c mu. C mu is 0.03. I mean 0.09. C mu is 0.09 by default. 0.09. Okay, K 1.5, and then you have this L. Okay, this is a mixing length. So it's a mixing length length scale. All right, so this mixing length scale, let's see. I should give you a reference. Okay, so you can see, okay, SimScale over here. It gives a very good rough idea of what this value should be. So it says that, okay, over here you should this mixing length scale, turbulent length scale, you should be about 0.07 times the hydraulic diameter, or in this case it's the diameter. Okay, so let's do this L turb. Let's do L turb here, and this will be 0.07, and 0.07 times what? This L pipe. Alright. Okay, this is not L pipe, it should be D pipe. Alright, D pipe. Now I'll just put this over here. Okay, upload it later. And also you'll find it in the video description. Both of these will be there. Then what is next? You'll need to calculate epsilon. And what is epsilon? Okay, 0.75. Okay, C mu to the power 0.75 times k to the 1.5 times where's k to the 1.5. Okay, then divide it by the mixing length. Okay, so you have this epsilon value, whatever thing here. Okay, so nuT. Alright, right, this one I kind of don't want to touch. I'll put it in let's see, let's give it a gray color. It's a warning, do not touch. Okay, do not touch, because there are formulas in there. Okay, Reynolds number also, I shall give it this color, and this one you can kind of touch, it's fine. Alright, very good. So nuT is equals to C mu times k squared divided by epsilon. And this will be 4.2 times 10 to the 5th. So I just put a green color to say this is like the final answer kind of a thing. So 4.2 times 10 to the minus 5 will be the value. It's almost 0, but just for the sake of thoroughness, you know, we don't leave it as 0. Alright, so let's do it. Let's put it in here. Spell amorous, cd0.original, go to nuTilda, and we'll give it a fixed value of uniform 4.2 times 10 to the minus 5. Let's give it a few more decimal places. Okay. See, what's the number formatting? Okay, at decimal place. Oh, it's really 4.2 times 10 to the minus 5. Okay, sure. Alright, so this is where is this? OpenFOAM RANS and the other ones here. Okay, let's give it 4.2 times 10 to the minus 5. 4.2 e minus 5. Okay, then the top patch is the outlet and the bottom patch is the inlet, so this is where I will do the pasting. Okay, Control Shift V, and this is for Linux systems again, and I can just do a very simple $sign internal field. So what does this do? It takes whatever values in this internal field and it puts it there. So I better get rid of the uniform, if not there will be some syntax error. Okay, so this is how we can structure it. The wall, we will have a fixed value of 0 because there should be no turbulence in the wall because the velocity is 0. So I mean, it's there's no turbulence there. Okay, open bracket. Excuse me. There you go. And this is what the spout amorous variable, roughly how you set up the conditions for the pipe. Okay, so a few more things. We need to make sure the other variables, they're not being messed with. So if you take a look at the k here, okay, if you take a look at the k, and this is LES, okay, or you take a look at nuT. Okay, what you notice is that the type here in this case, they are calculated. All right, these are calculated. So if you take a look at the nuT here, we should have calculated at the inlets and also at the outlets. What does calculated mean? Calculated means that I mean you don't exactly ask OpenFOAM to calculate nuT directly, okay? But the thing is, okay, that's wrong. Let me undo. The Control Z doesn't work here. Okay, and let me paste. Okay, that's better. Yeah. Calculated basically means that we don't do calculations. All right. I mean, OpenFOAM will do it is that OpenFOAM will check for, you know, am I calculating this turbulence viscosity, which is nuT? Am I calculating for it through any other means? For example, through nuTilda or k and epsilon. So if so, this nuT will not be touched in that sense. So this is a good way to, this is a good boundary condition to place this to put for nuT, so it kind of doesn't touch. Then over here we have a nuT wall function, which is probably a zero gradient or something. You can of course leave it as calculated as well, because you're not really messing around with nuT at all. It will be calculated through the k epsilon, or in this case a Spalart-Omerus model calculated. Okay, and actually all your k's, epsilon will be able to use this calculated boundary condition as well. Okay, I mean I should be doing changing for the other ones as well, the other case where I do the k omega SST. So what I'll do is I'll just write this in. Okay, this is a very easy solution, calculated, and the wave value is, I'll just put internal field. Okay, so I'll have to do it for all the ones here, because this is a Spalart-Omerus model. So I'll need to get rid of all of this. Okay, and that should do it. Hopefully there are no syntax errors, and basically I can just copy this whole thing. I can copy this whole thing and I will paste it inside the k entry, because I'm just going to use the same boundary condition all the way through. Okay, so that's done, and then I'm going to the omega entry, and I'm going to put exactly the same boundary condition. So maybe this is about 10 lines. I can just put dd. Okay, let's try again. 10 dd. Okay, that's better. And I'll paste it, and that's that should about do it. All right. So that's k, epsilon, and omega dealt with. nuT is also dealt with. So let's see, k is done, epsilon is done, and omega, it should also be done. Alright, so basically if we do a pimple foam run, everything should just do about right. Okay, so it will still run, it will do its thing, but yeah, Spalart-Omerus will do okay. Okay, and I'll need to do some editing for the k omega SST part, because cd0.original lets me change up the nuT and the nuTilda. Okay, so maybe this will be 13 dd, yeah, 13 lines, and I'll paste it here, exit, we are nuTilda. Okay, here maybe there are 12, I'm almost done, 12 lines dd. Okay, and paste, quit, and since this one uses k omega SST, epsilon will not be in use, so I can also delete this part. So maybe this one's 15, okay, 15 dd. Okay, just nice. Okay, so that's about it. And let's see, nuT done, nuTilda done. Okay, looks good, and this should be able to run. Okay, pimple foam RANS Spalart-Omerus. Okay, so Yeah, just gotta make sure I put it in a 0.original file and not in a 0 folder. Okay, so that's about that. Okay, so yeah, I am saving this here inside the file over here. Should be here under Intermediate Plus in the Spotlight Omerous. You should be able to find it here when you pull it down from GitHub. So let me just do a very quick push. Okay, git push, and you should be done. We should be done. Okay, I'll do an all clean. You can go and run the case yourself, because I'm not going to put a fully run case online. So git add and git commit and RANS k omega sst and s Spotlight Omerous bc case edited. Okay, and git push. Alright, so oh dear, I think I want to delete something. The pimple foam template. Okay, let me do a git reset. Git log one line, git reset 3fd 056e. Committed too much. Alright, right, let's see. Let's go to the template. Now do it all clean here. Okay, let's do it again. Git commit m RANS k omega sst and Spotlight Omerous complete. BC complete. Okay, and git push. Okay, perfect. Okay, should be able to get these files online now. I'll put it on the GitHub. So thanks for watching. I'll see you guys again. Bye bye.